All right, today is day one of what our Unit 2 is going to be. In terms of what it corresponds in the textbook, it's a blend of sections 4.1 and 4.4. What's going to happen in Unit 2 is instead of thinking about an angle as the piece of a picture of a triangle from a geometry book, we're going to look at it as a rotation in a coordinate plane. So first thing we need to know, an angle in standard position has its initial ray on the positive x-axis. That initial ray is rotated a certain number of degrees or radians, depending on what mode we're in. The position after the rotation is its terminal side. Positive angles are rotated in a counterclockwise direction. Negative angles are rotated in a clockwise direction. So for our first set of examples here, we're sketching in standard position, and we're going to determine what quadrant the angle lies, or where is the terminal side of that angle. So to be in standard position, we are starting with the positive x-axis or initial ray. That's a positive angle, so we're rotating counterclockwise. That's 90, that's 180, 200 is over here. So what we're going to do is draw a little arrow like that to indicate which way we rotated. When you name quadrants, you start in the upper right and you go around using Roman numerals. So it's quadrant 1, 2, 3, 4. So the terminal side of this angle lands in quadrant 3, so it's a third quadrant angle. Okay, what quadrant it's in is going to have a pretty significant impact on a lot of things we do in this unit. Next example. Negative 250. Standard position, we are starting with the initial ray as the positive x-axis. We are rotating around in a negative direction. So negative 90, negative 180, that would be negative 270. So we didn't quite reach there. Going to draw a little swirly to show which way it goes, like that. Quadrant 1, quadrant 2. So negative 250 is a second quadrant angle, because the terminal side lands in the second quadrant. Right, sometimes the rotation is more than one full rotation. For example, 420 degrees. Starting with the positive x-axis as the initial ray. Rotating in a positive direction goes this way. It would be a full 360 to get to here, and then we'd have to go 60 more. So it would land roughly there. Now, when you're sketching these out, you don't have to stress over where in the quadrant you're landing. As long as you're in the quadrant in terms of a rough sketch, it's good enough for this question as is. If this becomes a small part of a bigger problem, it might be good for scale purposes to be closer to the axis that it's really closer to when you draw it. But for this question as is, just landing in the correct quadrant is usually good enough. All right, now sometimes when you rotate, you land on an axis. So for example, a 90-degree rotation would land right on the positive y-axis. Okay, that's known as a quadrantal angle when it lands on an axis. So these are all examples of quadrantal angles where the rotation lands on one of the, I'm going to say 4 axes in terms of positive x, positive y, negative y. All right, so one thing that's happening in Unit 2 is we're moving away from an angle as a piece of a geometric figure and thinking about it in a more sophisticated way as a rotation in a coordinate plane. Okay, once you hit this area of math, or this area of trig rather, it becomes less and less common to measure degrees and angles, and more common to measure, angles and degrees, more and more common to measure angles and radians. When you guys get in calculus next year, whether it's here or at a college or university somewhere, highly unlikely you're going to do anything in calculus in degrees. Calculus is like hardwired to work in radians. Most of what we do from this point forward will be in radians, but not solely. There are some degree problems we'll still be dealing with, but primarily radians. Okay, so the conversion factor. if you know the degrees and you want to convert it into radians, you're multiplying it times pi over 180. So for example, 20 degrees, 20 times pi over 180, zeros cancel, 2 and 18 reduced to a 9, it's pi over 9 radians. Most of what we do in here, we will be leaving it as that exact fraction, pi over 9. It's relatively rare for us to be doing decimal radians. There are some problems where it's appropriate. We'll talk about it when we get there, but you definitely want to be comfortable in dealing with these exact fractions. Okay, going in reverse. If you know radians and you want degrees, you're multiplying by the reciprocal of that fraction, or you're going to flip it. So for example, we want to convert 8 pi over 5 radians into degrees. So it's that fraction times the pi over 180. That's just by the rule. The pi's cancel. We can reduce this down a little bit. That'll be 1. That goes into that 3. Brain freeze here. Let me do that. 5. I didn't finish my coffee this morning. I apologize for not being able to get that in my head. So it's going to be 8 times 36. 8 times 36 turns out to be 288. All right, a little bit more vocabulary. That's going to be pretty important to where we're working right now in trig. Coterminal angles. Coterminal angles are angles in standard position whose terminal sides are the same. Coterminal angles can be found by adding or subtracting multiples of 360 or 2 pi radians. So, for this first example, 40 degrees. One way, I jumped ahead. 40 degrees in standard position would look roughly like this. Well, what other angles would land in that same spot? Well, if we rotate it around another full circle, where 40 plus 360, 400 degrees, would land in that same spot, coterminal with 40. Well, what if we rotated in this direction? It would be 360 minus the 40 in terms of the absolute value, I explained that backwards. 40 minus the 360 would get us the negative 320. Rotating in this direction here, if we went a full negative 360, it would get us all the way to there, but it's 40 less. Okay, negative 100 degrees. If we were to sketch that in standard position, we're somewhere down here. Okay, what other angle or angles are coterminal with that? Well, we could rotate around 260 this way, or we could do another full 360 that way. In other words, add 360, subtract 360. All right, now 2 pi radians and 360 degrees are the same rotation. So if we have the same question, except in radians, instead of adding or subtracting 360, we're adding or subtracting 2 pi. So 7 pi over 6 plus 2 pi, give them a common denominator, there's a coterminal angle. 7 pi over 6 minus that same thing, coterminal angle. Negative example, add 2 pi, subtract the 2 pi, coterminal angles. All right, the significance of this. Why do we care about coterminal angles? Coterminal angles will share the exact 6 trig values. So I'm going to get my graphing calculator out here. This first one's in degrees, so I'll check my mode. I'm in degree mode. If I take the sine of 40, the sine of 400, the sine of negative 320, they're all the same number. Now, right now, you may be thinking, so what? They're all the same number, but that's going to have a pretty big impact on stuff we do when this becomes a small part of a bigger problem. Just as a quick rating example, with a different trig function, I'm going to go to mode, go into radian mode, clear that out. I'll use cosine this time for this. the cosine of 7 pi divided by 6, the cosine of 19 pi divided by 6, the cosine of negative 5 pi divided by 6. They're all the same number. Angles that are coterminal with each other will share the exact same values of all 6 trig functions. If we did the same thing with sine, if we did the same thing with tangent, if we did the same thing with cosecant, with secant, with cotangent, all the numbers would match up. All right, for the next slide here, it says if theta is an angle in standard position, its reference angle is the acute angle formed by the terminal side and the x-axis. Angles that share the same reference angles share the same absolute values of the 6 trig functions. And we have an example to illustrate this, and I already filled in the numbers here. So if we look at these angles right here, 10 degrees, 170, 190, and 350. Okay, we have one angle in each of the 4 quadrants, and the common feature here is that's 10 degrees away from the positive x-axis, 10 degrees away from the negative x-axis, 10 degrees away from the negative x-axis, 10 degrees away from the positive x-axis. That 10 degrees away from the nearest axis, and when we say the 10 degrees in this context, we're not putting a plus or minus. It's just like if you threw a protractor in that picture and measured it, it's a 10-degree angle. We're not taking into account a direction when we talk about reference angles. Okay, so they all share the same reference angle of 10 degrees. Well, if we take the sine of all of those angles, they all have an absolute value of about 0.174. If we take the cosine of all those angles, they all have an absolute value of about 0.985. Tangent of all those angles, absolute value of 0.176. Okay, what changes is the SIGN. The sine is positive. Oops, I don't know why I put just a 1 plus. We'll be consistent here. Or did I copy that wrong? Hang on 1 second, I apologize. Yeah, this is a minus, not a plus. I don't know why I did that. Okay, sine was positive in the first and second quadrant, negative in the third and fourth. Cosine, positive in 2 and negative in 2, but the pattern is different. Tangent, positive in 2, negative in 2, but the pattern is different. And we're going to get to why that pattern is what it is, I believe, next slide. All right, so one of the things you need to be able to do is, given an angle in degrees or in radians, identify what its reference angle is. How many degrees or radians is it away from the closest x-axis? And we're not putting an SIGN to this. It's just an absolute value. So 195 is down here. That's 15 degrees past the negative x-axis. So its reference angle is 15 degrees. Okay, 5 pi over 7. Well, in radians, the key stops along the way. That would be pi over 2, which is 90 degrees. Pi, which is 180. 3 pi over 2 is 270. And all the way back around would be 2 pi radians. Okay, 5 pi over 7 is a little bit more than pi over 2. Because 5/7 is a little bit more than a half. So, in standard position, didn't show the initial right here. In standard position, that's where it lands. It's a second quadrant angle. Well, how far away is it from the closest x-axis? Well, that means we'd have to get from 5 pi over 7 to 7 pi over 7. So it's 2 pi over 7 away. Okay, again, emphasizing why this is important in our world. If we were to take the sine of 195 and the sine of 15, they're going to have the same absolute value. Take the cosine of those two angles, same absolute value. Take the tangent of those two angles, same absolute value. Same story with secant, cosecant, cotangent. In radian mode, we take the sine of those two angles, same absolute value. Cosine of those two angles, same absolute value, so on, so on. All right. Next thing is, one of the things I led off with at the beginning of this PowerPoint was the fact of we're going to rethink how we treat an angle. Instead of an angle being part of a triangle geometry class, we're thinking about it as a rotation in a coordinate plane. Well, that means we're going to have to tweak the way we think about our trig functions. So in right triangle trig, this is how our 6 trig functions are defined, all in terms of opposite, adjacent, and hypotenuse. All right, now that we're going to be thinking about a rotation plane, we're going to tweak that. So what I drew is the simplest case of a triangle in the first quadrant. So if this is our theta, a rotation going from here to here, sine would traditionally be opposite over hypotenuse. But instead of opposite and hypotenuse, we're going to call it x, y, and r. The x is the x coordinate it takes to get to this point. The y is the y coordinate it takes to get to this point. And then r stands for the radius of the rotation. What happens is as this rotates around, it cuts a circle. That's the radius of the circle. Now, x and y change SI, G, and S's depending on what quadrant you're in. In the first quadrant, x and y are both positive. In the second quadrant, x is negative, y is positive. Third quadrant, negative, negative. Fourth quadrant, positive, negative. So, as you rotate around, the SI, G, and S's of the x's and y change. So that means that the positive, negative of the trig functions will change. So negative trig functions in right triangle trig make no sense because right triangle trig means you're in the first quadrant. If you're in the first quadrant, everything's positive. As soon as you start thinking about an angle of rotation in a quadrant plane, you potentially leave the first quadrant, and now your trig functions can become positive or negative. So what happens here is we get a nice little memory device. One of the more common ways that you see on websites and in textbooks is all seniors take calculus. I prefer one that's a little bit more fun. All seniors talk constantly. All 6 of your trig functions are positive in the first quadrant. Because what happens is if x is positive and y is positive, r is always positive. That's a radius of a circle. If all these are defined in terms of x, y's, and r's, and all positive, they all have to be positive. Okay, in the second quadrant, x is negative, y is positive, r is always positive. So what happens here is if sine is y over r, that's a positive over a positive. Sine is positive. If sine is positive, its reciprocal has to be positive. Okay, cosine is x over r. Negative over positive is negative. So cosine is negative in the second quadrant. If cosine is negative, so is its reciprocal. Tangent is y over x. Positive over negative is negative. Tangent is negative, so is cotangent. So the only 2 trig functions that are positive in the second quadrant are sine and cosecant. All the rest are negative. We can go through the exact same thing in this quadrant in terms of x is negative, y is negative, r is always positive. Set up all your fractions. Tangent and cotangent are the only 2 positive trig functions in the third quadrant. Everything else is negative. In the fourth quadrant, x is positive, y is negative, r is always positive. So when you set up all these fractions, it turns out cosine and its reciprocal secant are the only 2 angles positive in the fourth quadrant. Everything else is negative. All right, finishing up here with what types of problems are you responsible for from today. So the instructions are to find the exact values of the 6 trig functions for each angle in standard position. So for problem number 1, it's telling us the terminal side of an angle passes through the point 3, 4. So I already drew out a sketch for this. So the initial ray is the positive x-axis. Now, it didn't tell us which way to rotate. We don't care which way we're rotating because we already know coterminal angles share the exact same values of all 6 trig functions. So we'll rotate in a direction that makes the problem the easiest. Whether we rotate this way or that way, all the answers are still the same, because if they share that terminal, if they share that terminal side, they're coterminal, which means all the trig functions are the same. So if it passes through 3, 4, that means that length is 3, that length is 4. A squared plus b squared equals c squared, or recognizing as a Pythagorean triple, r must be 5. So once you know the x, the y, and the r, you're just setting up all 6 fractions. Okay, same type of question with a different wording. They're telling us the tangent of theta is negative 5/4. Theta is in quadrant 4. All right, if they didn't give us the second part there, and they just said tangent of theta is negative 5/4, that's not enough to definitely locate that particular angle. All seniors talk constantly. Tangent is positive in these two, negative in these two. So tangent being a negative number means that it's either quadrant 2 or it's quadrant 4. So in addition to that piece of information, we need to know more. Well, they were pretty direct. It's quadrant 4. So when we sketch this, it's going to be down here in quadrant 4. And again, it doesn't matter whether we rotated this way or we rotated that way. If it's coterminal, all the trig functions are the same. All right, now the tangent of theta is negative 5/4. That's y over x. Now, it doesn't guarantee that the negative is with the 5. The negative could be with the 4. Whether it's negative 5/4, negative 5 over 4, or 5 over negative 4, it's all the same value. You have to put the sign where it makes sense. So, did I draw this one backwards? No, I did not. I apologize. Again, I didn't finish my coffee. Okay, so the y value we know has to have a 5. The x value has to have a 4. In order to go right and then down, that has to be the plus, that has to be the negative. You do your a squared plus b squared equals c squared. That gets you your root 41 for your r value. So we know x is positive 4, y is negative 5, r is positive root 41. The x and y change SIG and S's depending on what quadrant you're in. The r is always positive. Set up your fractions, reduce, simplify, rationalize, whatever it is you need to do in order to get them in a final form. All seniors talk constantly, so we expect cosine to be positive and its reciprocal to be positive secant. All the rest of them are negative. All right, one more example for today. It's the same problem mechanically, but presenting the information in a slightly different manner. Okay, the cosecant of theta is negative 13 over 12. The cotangent is less than 0. Well, a strategy we did with a couple of other things is, if you don't like a cosecant equation, flip it to make a sine equation. Okay, this statement by itself is not enough to locate exactly where we are in the coordinate plane. Sine is positive. All seniors talk constantly, here and here. All the trig functions are positive in the first quadrant. Sine and cosecant are positive in the second quadrant. So we need something that breaks the tie between which of those two things. Well, cotangent is negative. Well, cotangent is negative here. So that means we're in the second quadrant. So when we sketch this, we have to sketch it as a second quadrant angle. So, second quadrant angle is landing us over here. When we draw our theta, it's always to the x-axis. That's using the reference angle thing we talked about. So when we sketch this out, it's a combination of using what we know about coterminals and what we know about reference angles. So the theta is always going to the closest x-axis. All right, so sine 12 over 13, you can do it as opposite over hypotenuse, or y over r. Well, we need a 5 to get a 5, 12, 13. If we're heading left, it must be a negative 5. So x is negative 5, y is positive 12, r is 13. X and y change SIG and S's depending on what quadrant we're in. R is always positive. Set up your fractions. Reduce, rationalize, whatever you need to do to clean them up. In this case, they're all good as is. So, if we are in the second quadrant, we expect sine and its reciprocal to be positive. All the rest of them are negative. And that is a wrap for today.